Welcome back to my lecture on climate change. My name is Stefan Rahmstorf and this is episode 2. And the episode 2 deals with the impacts of climate change and ways of mitigating climate change. In this lecture you will get a basic understanding how global warming affects the incidence of heat waves, droughts and floods. You will understand how global warming affects sea level, and you will understand the 2 degrees limit of global climate policy and by how quickly we need to reduce our emissions of greenhouse gases in order to stay below that magic 2-degree policy level. So there are basically 3 topics we will discuss in the coming half hour. Number 1, weather extremes. Number 2, sea level rise. And number 3 is the mitigation of global warming. In the episode 1 of this lecture, I have explained the basic facts of global warming and I have shown how the global average temperature increases. And of course, what will affect people most and ecosystems most is not the changes in average temperature, not the global average certainly, but their local temperature, but not even their average local temperature, but it's more the extremes that tend to affect people and ecosystems, and that's why we will have a look at weather extremes. This diagram shows the distribution of summer temperatures in Europe since the year 1500 AD, which can be reconstructed from various sources. And you will see here that on the right-hand side are the hottest summer temperatures, and the very hottest summers were 2010, 2003 and 2002 in that order. And on the left-hand side you see some of the coldest. You can fit a normal distribution, a so-called Gaussian distribution, to these data. This is what the black line shows. And you can see that the recent very hot summers like 2010 and 2003 really are way off to the right side. They are kind of outliers. And just this, the fact that the 5 hottest years were all in the last decade already shows you that this is not just some random distribution, but that you really see the effect of global warming happening here. I might add that such extremes have a major impact. The 2003 heat wave in Europe was later analyzed in detail, and it caused about 70,000 additional fatalities across Europe, mostly in France and Switzerland, where the center was. And in the 2010 heat wave, which had its focus more in the east, in western Russia, the early estimates were at about 55,000 additional deaths due to that heat wave. So we are talking about major natural, in quotation marks, disasters here. Now that is just one location, so it's limited information, but we can look at the global picture, and this is an analysis that we have done in my department, which shows how the observed number of monthly heat records, so these are record-breaking warm months, has increased in the last 10 years over and above what you would expect in an unchanging climate, a stationary climate, so a climate without global warming. And this is based on the analysis of about 150,000 time series starting in the year 1880. And what you see here is that everywhere where there's kind of yellow, orange, red or dark red colors, the number of heat records, record-breaking warm months, is several times larger than what you expect just by chance in an unchanging climate. And in fact, on global average, we now observe in the last 10 years about 5 times as many record warm months than you would expect in a stationary climate. So this is a very clear effect of global warming. We get about 5 times as many heat records in the monthly average temperatures as you would expect by chance. And as you can see, there are some areas where this goes even up to 20 times the amount of records that you might expect otherwise. So that means that global warming has not just affected the number of such heat waves in a small way, but rather it has affected in a major way And that's also consistent with a number of other studies that have shown that we get several times the amount of such heat waves as you would get without global warming. Now, often journalists ring us up if such a heat wave occurs and ask, now, is this due to global warming or not? And of course, we cannot answer this with yes or no, because it's a question of probabilities. And of course, also by chance, you could get such a heat wave. But as I just pointed out, the data analysis shows that if you looked at 5 heat waves, 4 out of those 5 would not have happened by chance, and only 1 of them would have been expected by chance. And that's why we concluded also specifically in a publication that for this Moscow heat wave, there was an 80% probability that this monthly heat record in July 2010 would not have been set without global warming. Now, what about other extremes and other climate parameters? I'm not even talking about extremes here, but about the annual average in precipitation. Because in many ways, rainfall is more important to us, certainly for agriculture, than the temperatures are. And the large map shows the observed increase or decrease in precipitation in Europe. Blue is increase and yellow is a decrease. And you can see that basically the Mediterranean countries have been getting a lot drier in the last decades. The smaller map in the inset shows you a typical model simulation here from a European Union funded project, which shows the change in precipitation in scenarios of enhanced CO2 concentration in the atmosphere as computed by a climate model. And there you can see that the climate model predicts exactly what we observe, namely a drying out of the Mediterranean region. And that's a pretty robust finding across a different range of models. Precipitation projections, by the way, are not robust everywhere. There are some areas of the globe where models get contradictory results because forecasting precipitation is quite a tricky business, but there are some areas where, due to basic physical effects, all models agree that it will get drier. These include, besides the Mediterranean, for example, South Africa, Australia, or the southwest of the United States. And all these are areas which indeed in recent years have been struggling with major drought issues. One of the problems with drought, apart from the effects on the harvest and agriculture, is the enhanced risk of fire. And an example of that were the major forest fires in Greece in August 2007, which you see here on the satellite image. You see the smoke from the fires on the satellite image. And these fires almost destroyed the historic site of Olympia that was just prevented in the last minute, luckily, because the winds changed. Similar example from Australia, where in the year 2009, in February, the worst death toll from bushfires followed a major drought, months-long drought and record-breaking temperatures, which contributed to those fires getting so out of hand. Now, the opposite of drought is too much water, and this picture, which looks like a work of modern art, perhaps looks quite pretty, actually shows Pakistan after the flooding in the summer of 2010 that was synchronous with the Moscow heat wave, the Russian heat wave. And this actually created the largest freshwater lake on the planet for a while, this flooded area in Pakistan, and it also followed record-breaking rainfalls there that were unprecedented in the rainfall time series in Pakistan. And these extreme events, the Moscow heat wave, the Pakistan flooding, prompted the World Meteorological Organization to issue a pretty unusual statement about the unprecedented sequence of extreme weather events, which it said fits what would be expected, is expected by the Ipcc, for example, as a consequence of global warming. And just yesterday, before I recorded this lecture, news came out, the analysis of the year 2011 by the National Oceanic and Atmospheric Administration of the United States, which found that 2011 will be remembered as a year of record-breaking extreme events as well. So this is all little pieces of evidence that show that the incidence of extreme events is increasing, not only heat waves, but also events like floods and droughts. And in a recent publication in the journal Nature Climate Change, we analyzed some of the unprecedented extreme events of the last decade, and found that there is pretty strong evidence linking extreme heat waves, extreme precipitation and droughts to global warming, whereas for some other things like storms, the evidence is less clear. Now I want to turn to the issue of sea level rise. Rising sea levels are a very logical physical consequence of global warming for several reasons. The first one is that if you warm up water, it expands, it takes up more volume, and that is what is happening to the ocean waters. And the second reason is that there is a lot of ice on land, continental ice, glaciers in the mountains, or the big ice sheets in Greenland and Antarctica. And if it gets warmer, the glaciers shrink, the ice melts, and this water ends up in the oceans, which also adds to rising sea levels. And that is exactly what the data show. We see here the global sea level measurements in the blue curve from the tide gauges, mostly in harbors, that have been measuring sea level, some of them actually for several centuries back. And the red curve shows the global measurements from satellite, which started in the year 1993. Now you can see that these measurements show that sea level since the late 19th century has risen by 20 centimeters. And you can also see already in this diagram that this rise has been accelerating. The rate of rise in the beginning of the 20th century was around about 1 millimeter per year, whereas towards the end, in the last 20, 30 years, it has been about 3 millimeters per year. One of the contributions to the sea level rise comes from the big ice sheets, and I want to show you this here in this diagram, which shows in the blue and the green curve the contributions of the Antarctic ice sheet and the Greenland ice sheet, and in the red curve the sum of the two to sea level over the last 2 decades. And you see that in the 1990s the curves are rather flat, so the ice sheets didn't contribute very much, but then the ice sheet contribution to sea level rise accelerates markedly and is increasing quite steeply. The photograph on the bottom left, by the way, shows a meltwater lake on Greenland. It looks very beautiful, but the increase in the number of these meltwater lakes and other signs of melting at the surface, of course, is a real concern because of the effects on sea level. This actually is doubly a concern because we know that the Greenland ice sheet has a critical limit, and if you warm it above that temperature limit, it will melt down altogether because a vicious circle will kick in. The ice sheet will get lower and lower. It is now 3,000 meters thick, and by lowering, it automatically gets into warmer parts of the atmosphere because the atmosphere gets warmer as you get closer to the surface. And therefore, there is a critical threshold, which we call a tipping point, beyond which the Greenland ice sheet will be doomed to melt down altogether, which will raise the global sea level by about 7 meters. Now, luckily, this will take some time, probably several thousand years, to reach its full force, to melt down altogether. But the worrying thing is that already within the next 50 years or so, we could push the Greenland ice sheet beyond that tipping point, so beyond the brink where then it is practically almost impossible to stop the further ongoing melting for many centuries to come, and therefore ongoing sea level rise for thousands of years into the future. The latest studies also calibrated with data from the last interglacial. There was a last warm period about 120,000 years ago between 2 ice ages. This latest study shows that this critical threshold where Greenland might melt down altogether may well be below 2 degrees global warming, the policy target that we will come back to later on in this lecture. Now, the sea level rise in the last couple of decades is proceeding faster than expected by the Intergovernmental Panel on Climate Change. So that's another point where the IPCC has actually underestimated the change, and it's happening faster than the models predicted. You can see that here the blue range is the projections by the IPCC starting in 1990, which projected a sea level rise since then by roughly 2 millimeters per year, whereas the actual data show it rising at about 3 millimeters per year, so much faster than expected. The red line is the satellite data, and the orange line is the data from the tide gauges. Now, how does this sea level rise correlate with global warming? I already mentioned there is a very simple physical reason why global warming must lead to sea level rise, but is there more to it? Can we say more about this connection? And indeed we can. If you think about it as a physicist, which I am, and that's how I approach this, you would expect that the rate of sea level rise should be proportional to the amount of warming. And that is indeed the case if you look at the last 130 years, which you can see here. The red curve shows the observed rate of sea level rise, and you can see this here going up from about 1 millimeter per year on the scale of the left to more than 3 millimeters per year over the last 100 years. I mentioned that fact earlier. But the gray curve here, that actually is the global temperature curve, which also goes up in a similar wave-like fashion as we saw in episode 1 of this lecture. And the two look already by eye, they look quite correlated, that the rate of sea level rise went up in the 1930s to 40s when the temperature also rose. Then there was this plateau in the global temperature for a few decades when the rate of sea level rise also stagnated. And since about 1980, temperature goes up again, and so does the rate of sea level rise. And the blue curve, the blue range here, is actually a slightly refined model, a simple equation that links the global temperature change to the rate of sea level rise, and you can see they very closely match here. Now this is a correlation that you would physically expect and that you observe for the past. And so what if you use this to predict the future sea level? That is what is done in the next slide here. The colorful areas here show this exercise for 3 emission scenarios. I already mentioned that we don't predict temperature, but if you give us a certain amount of CO2 concentration in the atmosphere and other greenhouse gases, we can say how much warming will there be, and that is quite robust because it follows that simple energy balance of our planet. And if you know how much warming there will be, with a simple formula that connects the rate of sea level rise to warming, you can work out how much sea level rise to expect. And as you can see here, the best estimates for these 3 emission scenarios shown here range between 1 meter and 1 meter 40, with an overall uncertainty range between 75 centimeters and in the uppermost extreme up to 1 meter 90 by the year 2100. Now, that is based on this correlation from the past. The IPCC in its last report tried to predict sea level rise based on models for mountain glaciers, for the thermal expansion of the ocean, for the behavior of the ice sheets, and ended up with much lower values, which are shown in the bars on the right-hand side there below the colorful areas, labeled AR4, that stands for Fourth Assessment Report. You see the range projected by the IPCC, which is between 18 and 59 centimeters, so much, much lower than those so-called semi-empirical projections. Now, a lot of members of the sea level science community, including myself, actually consider these IPCC projections implausibly low for several reasons. Number one, the IPCC already underestimated the past sea level rise, as we showed in the earlier slide. Number two, you get into the middle of these IPCC projections even if you simply continue the rate of sea level rise observed in the last 20 years without any acceleration. But in the past, sea level rise has gotten faster the warmer it got. Why should that process suddenly stop and we should just continue at a steady rate in future despite massive warming? That's just implausible. And the third aspect here is that these relatively low IPCC projections are based on the assumption that the Antarctic ice sheet is going to gain ice mass over the next century, which largely compensates the ice losses from Greenland, so that overall the two big ice sheets contribute virtually nothing to sea level rise, whereas the observations show that already both ice sheets are losing ice mass at an increasing rate. That is why, unfortunately, I'm personally convinced that the Ipcc projections are low, and it's more likely that we end up at much higher sea level rise by the end of the century. Now, it would be nice to know sea level further back in time in order, for example, to calibrate this empirical relationship between sea level and temperature. And such efforts have been made and are still underway, and I'm also part of a project that does that by coring in salt marshes on the coast, which record a history of sea level of the last thousands of years. And here on the Outer Banks in North Carolina, in these photos, you see how this coring is done. You can go several meters deep into the peat there and take out cores and analyze from these peat cores how fast sea level has risen in the past. And a first major result of this coring in North Carolina is shown in the blue curve here, which gives us a sea level history over the last 2,000 years. Now, this first and foremost is a local history for North Carolina, but we believe, because sea level is connected worldwide, it cannot deviate too much between different places on Earth, and we believe that the deviations between the global mean sea level and the local conditions in North Carolina are at most plus or minus 10 centimeters over the last 2,000 years. So that, to a first approximation, that should also reflect the global sea level evolution. So what does it show? We see sea level pretty steady between the birth of Christ and the medieval age to the year 1000 AD, then a slow rise by about 0.6 millimeters per year up to about the year 1500. After that, sea level is steady again until the modern 20th century rise begins, which is about 3 times faster than any sea level rise we find for the last 2,000 years here. And this, for the last 1,000 years at least, can be understood very well with the help of the global mean temperature and this very simple formula that I mentioned earlier, the result of which is shown in the red curve here, which very closely reflects the sea level evolution over the past 1,000 years. So we have used this approach also quite recently to project a bit further into the future, up to the year 2300. And on the left-hand side, you see how the rate of sea level rise changes in various scenarios, emission scenarios. On the right-hand side, you see the overall sea level rise. And I just want to highlight one point here, namely that if you assume that we manage to limit global warming to 2 degrees at most, so this is this famous policy target of 2 degrees, even then, the good news is that we managed to limit sea level rise below 1 meter by the year 2100. We're pretty certain to end up below this. But by the year 2300, we will get between 2 and 3 meters of sea level rise, even after stabilizing global warming at 2 degrees above the pre-industrial temperatures. And this basically illustrates the very long response time of sea level. Sea level rise is a process that starts off very slowly, but then it's virtually unstoppable for many centuries to come, even after we have stopped global warming. This slide illustrates the 2-degree limit of climate policy, and you see it here compared to some of the emission scenarios for business as usual, which do not assume a stringent climate policy, and these scenarios invariably end us up above the 2-degree target. And so that means that in order to stay below those 2 degrees, we really have to implement stringent climate policies. And this 2-degree limit was adopted by the European Union already in the 1990s as its policy target, and the European Union has also succeeded to reduce its emissions somewhat in the last decades. And the 2-degree limit was adopted by the world community, the nations of the world, at the Cancun Climate Summit in the year 2010. Now, we already mentioned that sea level rise is probably going to be a major issue even if we limit warming to 2 degrees. So the target might be too high, but that is not for climate scientists to say, but it's rather a discussion, a broader societal discussion. So setting a target like this is not a scientific question, it's a policy question. And I should also mention that the small island states and the least developed nations in Cancun pressed for a lower target of 1.5 degrees, which obviously for the small island nations would be better, because even with 2 degrees of warming they run a serious risk of being wiped off the map, so to speak. Now, the question to natural scientists again is, once such a target is set, how much CO2 emission does this still allow us? And we can illustrate this with the next slide here, which shows 2 extreme scenarios of a bundle of future scenarios that have recently been developed. The blue one is a scenario that keeps us with a good probability of about 2/3 below the 2-degree target, whereas the red one is a kind of worst-case emission scenario where the emissions continue growing until the end of this century before they are then leveled off and reduced. And you can see there's a huge difference in temperature. That's the right-hand graph, where the unabated emissions lead us to a world with about 8 degrees global warming versus less than 2 degrees in the blue emission scenario. Now, the blue emission scenario overall until the end of this century would allow us to emit less than 1,000 gigatons of CO2. That is less than 1,000 billion tons of fossil CO2. And by the year 2050, in order to stay below the 2 degrees, we would still have a leeway of emitting about 750 billion tons of CO2. Now, the reason why this is a lump sum that we are still allowed is the long lifetime of CO2 in the atmosphere. That is a really fundamental point to understand. There is no safe annual level of emissions that we say, okay, in the future we can forever emit 3 gigatons per year or so, and this will be safe. The only safe limit in the long run is 0 emissions. And in fact, this blue scenario even has slightly negative emissions, assuming that we manage to soak up a certain amount of CO2 from the atmosphere. But the key point to remember is that the CO2 we emit today, a large fraction of that will still be in the air in hundreds of years, even in thousands of years. And that's why the total amount we can emit is limited. And if we want to stay below 2 degrees, then this is limited to about 750 billion tons by the mid-century and less than 1,000 billion tons by the end of the century. And that is quite a tight budget, because at the current rate, we will have exceeded or used up this budget in less than 25 years. So what this really shows us is that stopping global warming at an acceptable level, say below 2 degrees, is really a race against time. And the reason why it has become a race against time is because we did not act early enough. For example, 20 years ago in 1992, the Rio summit decided to stop global warming, to stabilize the greenhouse gas concentrations in the atmosphere at a safe level. But the emissions did not decrease after that, but rather they increased and increased further. And by now, 20 years later, it is not enough to slowly reduce emissions, but we really have to hit the brakes on full and reduce our emissions really fast. Like in the blue scenario here, if we want to have a good chance to limit global warming to a maximum of 2 degrees. Now, this may sound pessimistic, but it is the reality as far as science can discern it. And there are ways of reducing our emissions fast enough without major economic problems. And these are explained in the further lectures in this series. Here in this episode, you will find a few more exercises for self-study to go deeper into a few of those issues that I dealt with here. And I thank you very much for your attention.